Every day, this Swiss highway bears tens of thousands of vehicles, carrying thousands of tons under constant traffic. Normally, resurfacing would shut it down for months, but Swiss engineers devised a brilliant solution. A mobile construction bridge system, precisely engineered to support real traffic loads while the road beneath is completely removed and rebuilt. How did they make the impossible possible? Let's find out. The Astra Bridge is a revolutionary mobile construction bridge, engineered by Swiss experts for highway maintenance. While road work happens underneath, traffic continues to flow safely over 2 lanes at speeds up to 60 kilometers per hour. Its standout feature is mobility. Mounted on wheels, the bridge can be transported and installed by truck, making relocation between construction sites effortless. Another major advantage is rapid deployment, fully assembled and operational overnight, allowing daytime construction without lane closures or traffic diversions. This ingenious design minimizes disruption while keeping highways running smoothly, showcasing Swiss engineering at its most efficient and innovative. The bridge is meticulously designed by engineers using advanced CAD/CAM software, with every steel girder, load-bearing rib, and connection modeled to millimeter-level precision before a single weld is made. Its entire structure is pre-calculated for load capacity, deflection, and torsional behavior. The main frame is fabricated from high-strength steel plates, formed into large modular sections in the factory. Components weighing tens of tons are positioned with specialized lifting equipment, then joined by skilled welders completing thousands of meters of continuous welds under strict conditions. Every joint undergoes visual inspection and non-destructive testing, ultrasonic or dye-penetrant, to uncover even microscopic defects hidden within the metal. Before being transported to the construction site, the bridge undergoes rigorous outdoor testing in the yard. The entire structure is activated and moved across concrete, simulating real working conditions, while engineers monitor stability, steering, and the response of the frame and wheel assemblies under load. Only after passing every test is the mobile bridge approved for transport and installation, ensuring it can safely operate in real traffic without interrupting the flow of vehicles above. The completed Astra Bridge spans 256 meters, including a 100-meter elevated section that allows construction directly underneath. With a clearance height of 3.1 meters and an underbridge width of 5.1 meters, construction vehicles have ample space to operate while traffic flows above uninterrupted. Before installation, the entire assembly was carefully simulated to prevent errors. Traffic on the motorway was temporarily reduced to a single lane, guided along the emergency shoulder. The bridge system arrived in 47 heavy-haul trips, each carrying a precisely sequenced component. Compressing a 2-lane steel motorway bridge into a transportable configuration required modular components that could fold and rotate on-site. Motorized elements, like the upper halves of the ramps, could unload themselves using an integrated hydraulic system, streamlining installation and minimizing disruption. Lighter, non-motorized elements were lifted into place by cranes, while the installation sequence began with the lower ramp sections, followed by the curved transition modules connecting the road surface to the bridge deck. The upper ramp halves were then precisely driven into position, millimeter-accurate, joined, and secured with bolts to form a single, unified structure. After each step, the control systems of all modules were synchronized via software, ensuring the bridge operated as one integrated unit. The lower ramp sections received hydraulic oil from the upper ramps and, in theory, could move independently. In the curved transition modules, lower ramps rest directly on asphalt, while other components are stabilized by large steel base plates. The central bridge consists of intermediate segments and motorized portals, connected by load-bearing pins. On the first night, both bridge ramps were completed, allowing daytime traffic to flow in 2 lanes. On the second night, cranes operating on the bridge deck completed the full structure. Maximum gradients reached 6.1%, and the deck rose to 3.6 meters when the 4th portal was installed. Each portal required about 30 minutes to unload and prepare. While every step was meticulously planned on paper, only real-world construction revealed whether the design would work as intended. In April 2022, the first deployment of the Astra Bridge on the A1 motorway officially began. Over 20 heavy-haul transport vehicles simultaneously departed the staging area, each carrying a bridge module. From that moment, every minute counted. A section of the motorway had to be fully closed for 2 consecutive nights. The challenge was clear: within 14 hours before 10 a.m. on Sunday, a fully operational bridge capable of carrying traffic had to be completed in the first hours. The 2 ramp sections were positioned and precisely connected, while cranes lifted and installed intermediate modules under extremely tight site conditions. Every movement, vehicle placement, crane angles, and installation sequence was meticulously planned. Each assembly, consisting of a bridge portal and intermediate module, could occupy the construction schedule for no more than 30 minutes. To save time, the bridge was assembled simultaneously from both ends. Once in place, components were secured with high-strength bolts and electrical connections, forming a single, fully integrated structure capable of supporting real traffic loads immediately. At that very moment, the construction crew began their road rehabilitation shift. A milling machine lowered its cutting drum into the old asphalt, removing the pavement to a precisely calculated depth. Meter by meter, the roadway was processed in a stable, controlled manner, with the milled material neatly conveyed behind the machine, exposing a fresh base for the next stages. Immediately after, an industrial sweeper moved in, using rotating brushes and a vacuum system to collect all remaining dust and debris, thoroughly preparing the surface for asphalt resurfacing. This sequence was repeated in perfect sync with each movement of the bridge system. In areas machinery could not reach, workers manually treated the surface with saws, jackhammers, and compacting tools, refining edges with precision under tightly controlled conditions. To remove any remaining weak spots in the base layer, dust and loose material were continuously collected, gradually revealing a uniformly roughened surface that met technical specifications. After surface cleaning, the crew heated joints and milled edges with gas torches to eliminate moisture and activate material adhesion. Hot bitumen compound was then injected directly into the joints, penetrating even the smallest gaps to form a flexible, watertight bond. Next came the tack coat application and placement of the new asphalt layer. Hot bitumen was fed from tanker trucks through flexible hoses, supplying the paver continuously to maintain stable temperature and flow. The sprayer and paver moved slowly beneath the bridge, evenly laying asphalt over the prepared base. A dump truck reversed beneath the bridge, raising its bed to release hot asphalt in a controlled flow, while workers guided and leveled the material by hand to ensure consistent thickness. As the asphalt settled, excess material along the edges was adjusted, keeping the layer uniform, well-confined, and ready for traffic. Moments later, the fresh surface was ready for compaction, while traffic continued flowing just meters above. A finishing and cleaning unit moved over the newly laid asphalt, using rotating brushes and suction to remove loose aggregate and excess material at the same time. Workers manually refined edges with handheld air blowers, ensuring a clean, uniform texture before final compaction and curing. Next, the final stone-mixed asphalt layer was placed on the roadway paver. The paver was aligned to the correct elevation and centerline, with heating, drive, and grade control systems activated. Hot asphalt mix was continuously supplied from tanker trucks outside the work zone, transferred via smaller vehicles, and carefully loaded into the paver hopper. The supply process was meticulously controlled to maintain consistent temperature and material uniformity, ensuring a flawless final layer. The asphalt is discharged directly into the paver's hopper, ready to be spread onto the road surface. As the paver advances slowly and steadily, internal augers distribute the mix evenly across the full lane width, while the rear screed levels the surface, setting precise thickness and profile. Workers monitor edges and layer thickness closely, ensuring a continuous, smooth paving operation beneath the confined space of the bridge. The final asphalt layer forms a uniform surface, ready for compaction and reopening to traffic. Compaction is performed using vibratory road rollers, moving slowly in multiple passes according to a pre-planned sequence to achieve the required density and structural strength without marks or deformation. Thanks to the Astra Bridge's stable structure, compaction proceeds normally while traffic flows uninterrupted above. The Astra Bridge represents an innovative solution for maintaining and repairing roads without traffic interruptions, saving time, money, and improving safety. However, Rental costs are high, $10,000 to $20,000 per day. Critics argue that, in 14 hours, traditional repair methods might have been completed. Yet the bridge's value lies in minimizing disruption, enabling continuous traffic flow, and creating a safer, more efficient work environment, benefits that conventional methods cannot match. The use of non-stop mobile bridges for road maintenance remains a very new solution and has yet to be widely adopted in many countries. Traditional open-air repair methods, closing roads, diverting traffic, and working directly on the pavement, remain the most common approach due to lower costs and familiar procedures. This contrast fuels ongoing debate, balancing technological innovation against practical realities in infrastructure construction. The first step in the resurfacing process is milling the old asphalt layer, usually 2 to 10 centimeters deep depending on the level of damage. The milling machine grinds the asphalt into small pieces, conveys it onto a belt, and loads it directly into trucks. Only the worn top layer is removed, preserving the underlying base and structure. This avoids full reconstruction, reducing costs and significantly shortening construction time. The milled asphalt, known as reclaimed asphalt pavement, is then transported to a recycling plant for reuse. The recycling plant, the reclaimed asphalt pavement, RAP, passes through a screening system to sort particles by size and remove impurities such as soil, oversized stones, or metal. The usable asphalt particles are blended into uniform batches, a critical step because RAP can have varying levels of aging after years of service. Proper sorting ensures the recycled mix performs as well as new asphalt. Once sorted, the RAP is combined with new asphalt binder, fresh aggregates, and a rejuvenator, which restores the elasticity of the aged binder. At the mixing plant, the RAP is gradually heated to prevent burning, then mixed with hot binder and aggregates according to a precise formula. Modern asphalt plants can incorporate 30 to 60% RAP while producing a high-performance mix equivalent to brand new asphalt. This step is crucial because it conserves natural resources, reduces CO2 emissions, and lowers overall construction costs. Before placing the recycled asphalt layer, the roadway must be thoroughly cleaned of dust, dirt, and debris to ensure maximum bonding. In this modern process, a single machine performs both tasks simultaneously. As it moves forward, front nozzles spray a thin layer of bonding material, the tack coat, directly onto the old pavement using asphalt emulsion or liquid asphalt. This layer acts like glue, helping the recycled mix adhere tightly to the existing surface and preventing slipping or separation under heavy traffic. Immediately behind the spray bar, the same machine places the recycled asphalt mix onto the tack-coated surface without delay. The paver spreads the hot mix to the design thickness while its screed vibrates and compacts continuously, forming a smooth, uniform layer with proper initial density in a single pass. Afterward, vibrating and static rollers complete compaction to achieve the required density, preventing rutting or cracking. Once compaction is finished and surface smoothness is verified, the roadway can be reopened, performing just like new. That wraps up our look at the modern road repair process in Europe, where advanced technology addresses traffic flow and safety challenges simultaneously. From the mobile Astra Bridge to every construction step carried out underneath, each detail is meticulously planned to minimize disruption and maximize efficiency. This isn't just a story about road repairs. It's a glimpse into a smarter approach to infrastructure management in Europe. The information in this video was compiled from multiple sources, so if anything is unclear or needs correction, please leave a comment. We welcome discussion and feedback to improve the content. Please join the Mana Tech Explorer and watch the next videos for more content.